So, welcome to Chapter 16, where we're going to look at regression models for when the relationships aren't straight lines or what we call linear. These are nonlinear relationships. And when we look at these nonlinear relationships, we're used to seeing where an x would have a direct impact on y. Associated impact is an x goes up by a unit, y has an associated unit increase. Now we're going to start looking at different levels, things called polynomial, where we take an existing independent variable and raise it to a particular power, squared, cubed, fourth power, and so on. We're also going to look at log transforming models, transforming using a log function, both the x or the independent variable and the y side. The intent of all this is to increase the predictive power, increase the r squared adjusted in the cases where we have that, but also so that we can see decrease in the amount of overall variation that's left to chance. That's associated with the r squared, with a coefficient of determination. So from the past, what we've seen is something like this. We saw this in Chapter 15. We have a situation where someone's analyzing the rental market in Michigan. They have data, they look at the rent, the number of bedrooms, the number of baths, and the square feet. And what they're trying to do is evaluate the model to predict rental income when something new comes on the market or we have to reprice. Well, from a simple standpoint, what we've done up to this point is take a look at the rent. We have 40 observations, and we would run the regression, regress rent across bath, bed, and square feet. And what we got was something that had an R squared of about 79.32%. So 79.32% of all the variation in rent can be explained by what's happening in bed, bath, and square feet. The model itself would have been significant. The independent variables, are they significant at 5%? Well, bed is, square feet is, but bath is not. So two of the three are. That's how we would normally run across this kind of thing. Now, as we'll see as we go forward, we might want to look at it another way. What is another way? Well, to start, we're used to seeing something from a linear regression standpoint. For example, a simple linear regression, 1x to 1y. We see a unit increase in x. We expect y to change by the beta of 1, and then associated with it multiplied by the value of x. It gives us a magnitude. However, sometimes you can't have a straight line. In Chapter 15, as we saw, we put a restriction of something being linear on things, but now we might want to look at what happens if we take x and possibly square it. But realize this, we're always going to include x by itself, at least from the start, and then try adding things associated with x, like an x and an x squared. Typically when we see something, an example, when we see affirms the cost of doing things, based on economies of scale, we often see the costs drop initially, but over time those begin to rise. And what we see is a quadratic relationship where we're comparing y to x, but in this case we believe that there's a curvature that's happening. Either it's increasing then decreasing, upside down U, or it's a U shape. It's decreasing then increasing. Again, this is a model. There's error in this model. So when beta 2, so we associate beta 2 that goes with when I square x. Still, it's only one variable is x, but I'm using it in two different ways. When beta 2 is positive, we see an increasing function when beta 2 goes up and comes down. So say we had a look at something. We want to estimate the relationship between cost and output. So we've got 20 examples of firms and their output and their average cost. And if we just looked at something like this, and we'll see the example here in a bit, the dots represent the actual data. Now, a straight line would be the simple linear regression versus, and then the curvature makes it try to fit a little better. Again, this is all about fitting best to your data so that we can decrease the variation and increase our r squared or r squared adjusted so that we leave less to chance in our prediction. This seems to have somewhat of a curvature. It may even reflect a first down, up, and another curve. Maybe we need to move it to a cubic. We'll see that in a bit. So what we would like to do is take something where we look at cost and output and see if we can find some kind of relationship. On the Excel sheet here, let's look at this. We'll look at cost. Well, first thing I want to do is show you output versus cost. So what I've done is plotted the output level and cost. Output along the X, cost along the Y. So that we can see these kinds of relationships being fit. And like anything else, if I want to, I can right click on a dot and add a trend line. The linear trend line goes straight, and then you can play with polynomials. So the polynomial trend line will be like this. But if I go and try to play around with it some more, as we'll see over time as I click on the line, maybe I want to raise that to a power. And we'll see how do we do things like this as we move over time. If I display the equation on the chart, you can see now I have a cubed term to it. So let's take a look at that. How does this play out? So I have output, and what I've done is taken a look at output and squared it so that I can have a relationship that implies x and x squared, each with a different beta. So what I've done is taken output, and I've actually just squared it. 4 squared is 16. And I've run the regression, and we've run the regression many times by now. And the first regression I ran was just simply output versus cost. Can output predict cost? So I run the regression, and here's what I get. I get an r squared of near 0. So not a lot of variation in cost is being explained by output. It's not significant because this is bigger than 5%. 84 is bigger than 5, so we wouldn't reject the null. This is not a significant regression. So then what? Let's square it. So now I've run the regression again with output and output squared, and what do I get? I haven't adjusted r squared since there's two variables in it. Even though I'm using only one variable, I'm actually using as two separate terms. I'm describing 45% of it. So 45% of all the variation in cost can be explained by output and output squared. Notice output and output squared are in here. The regression, it's significant because this is less than 0.05, and the two p-values are both less than 0.05. So they too are significant. Remember, the intercepts p-value has no purpose here. It's nothing more than a balancing item. It can be significant or not. We're not worried about it. Again, both of the confidence intervals that we saw in Chapter 15 don't contain 0. So what we found is that. And now that we have this estimated regression equation, and you can see the intercept is 10.5, and just to confirm, 10.52, negative 3, and so on, here's the estimated regression equation. Now, if we say if somebody produces output of 7 million units, you put 7 in here and 7 squared in here, and you get a predicted average cost of 9.4. You're not going to be able to predict outside of anything you've seen. So over here, with the output, it has to be within the bounds of what is the max and the min. So the minimum value is 4, and the max value is 11. So you cannot predict anything outside of 4 and 11. So 4 and 11 inclusive. Anything outside of that you've never seen before, and the regression isn't sufficient, at least for this part of statistics. The thing is, you're looking at the effect that's happening here. So when there's no quadratic term at all, you can just see the direct relationship x to y. However, and you can see where the inputs would be max and min based off of that. But if you want to look at the effect, at least the marginal effect of it, take a look at the two parts of the right-hand side of the equation, x and x squared, b1x plus b2x squared. Remember in calculus, as we try to do some minimizations here, and this is not calculus class, but what we would do is simply take the derivative. Get rid of x, bring the 2 in front of 2b, and you get this. Now, what's the point of all this? I'm not here to teach calculus. I'm here to show you something rather clever. Once I've taken the derivative of that level, what I'm going to do is set that equal to 0. So I set this equation here to 0, and this is what I get. X equals negative b1 over 2b2. If b2 is less than 0, you're going to find the maximum value for the equation that you'll find, and b2 is greater than 0, you find the min. So if we go back a second, b2, in this case, we have to find out what we're doing here. b2 would be output squared, and we're going to see the leading coefficient be positive. With it being positive, it's going to find a minimum. So from this equation we just had, plugging in the values for b1 and b2, you know that the minimum cost is obtained at 7.32. That's the lowest predicted minimum cost you can get. go back to your data, and from this, you're not seeing this in the average cost. It's something that we're going to have to predict. That's telling you, based on the data that we have, that's the minimum one we'll see. We can also talk about higher orders beyond 2. Now we're talking cubing it. Can I move to a cubic relationship or a cubic regression? Sometimes we have to work through this, and sometimes we can actually see benefit from it. We took 9, got 81, 9 cubed is 729, and so on. Going back to that total cost model, if I cubed output, look what happens. My adjusted R squared jumps from having the quadratic from 45 to 85. That's a massive jump. That leaves less than 15% of all the variation in total cost to chance. That's amazing. Significance of F, that's good. And all of these are good. So everything is significant, and we have a more predictive, more stable, better fit model just by cubing. Those kinds of things are important, and you can see from the relationship, it's still a single variable output, but all I do is take it by itself, square and cubed. The real last bit that we'll get into here has to do with what happens if we are starting to look at relationships that don't have that feel of cubic, quadratic, and so on. Oftentimes what we do is do a transformation, in this case a log transformation. And there's different kinds. You can take a log of the x's, you can take a log of the y's, and you can take a log of the x and y simultaneously. And what we're trying to do is get away from the linear assumption that we have. Oftentimes we go right with that in regression, seeing these simple unit increases in y based on x. Sometimes we might want to see something different. For example, a log-log model. Take a log of the x and log of the y, and the point of this is to simply create better fit. So I take the natural log of both. And what I would do is simply do that, and with it, we're just going to see an increase. So in this case, since it looks like a regular regression equation, we can run it as a regular regression equation once I've transformed them in their usual state, run the regression, get the results, and then raise them to the exponential power of e, and then what the result would be back in the value of x. We'll see that here in a bit. And you can see these relationships. What it does is helps you view your data and which model you might want to pick. So in this case, because it looks like regression, a 1% increase in x, well, B1 shows elasticity. So as I increase x 1%, that means it will see a 1.2% decrease in the demand, which comes from y. That model, because we're having to raise this back up to get it to like terms with x, so you would take the ln of y, raise it to an exponential power here, I have to add back the standard error to get it to the model state. I know it's a little complicated. For our sake, we're just going to put it back in so that we have a more predictive model, more accurate model, and it's simply the standard error that's created in each regression. So you take this model, add in the variance divided by 2, and that gives you standard variance divided by 2, and that gives you the value you need to get back to y. Here's the outcome. You're given standard error. You can see how we would play this out. Show it here in a bit. Another one is a logarithmic model. It's a logarithmic model because we're only dealing with the x side. The y is left alone. In this case, there is no transformation on the back end. You can truly see an x to y relationship, except that because we're dealing with the log value of y and we're doing a reduction in that case, the beta has to be divided by 100 just in its interpretation. It's a unit change. So it's in terms of percent, that gives it to a 1 over 100 or 1%. It's kind of like the last one when we saw a 1% change. But in this case, there's no transformation. Very similar model. We'll look at this in Excel in a bit. An exponential model, nothing happens to the x, everything happens to the y, natural log. It's just another kind of model. And in this case, you have to do the transformation once you've run the regression, add back in the standard variance, standard error squared divided by 2, raise it to the e power, and you get your value. Every one of them has a reason for doing it, and the reason is we're just trying to best fit a model. In doing this, it gives us the power to take data that we currently have and play around with it a little bit to get to to derive a solution that gives us exactly what we need. Going back to the Michigan problem with the properties, we had 40 properties. We knew the number of baths and bedrooms and floor space, and we looked at rental price. Well, after doing a little bit of work, plotting beds against rent, plotting baths against rent, it looked like those models might be more linear, maybe a little exponential, but when we looked at square feet versus rent, it became a little bit logarithmic. So let's try different kinds of models. Let's try when we do a general, this multiple regression. In this case, we're going to take the natural log on one side, so it's a log model. When we take the natural log here but nothing over here, it's going to be an exponential model, and this is a log-log model. Back in Excel, excuse me, start with the first model. I just ran the regular regression, and we got a model that had an adjusted R-squared of about 79. It's significant, and all its variables were significant except for bath. Remember that, bath is not significant, but it is significant by itself. The next one is when I take a log model by logging square feet. So I took a log of this natural log of the square feet, ln of the value of square feet, ran the regression, and I got an adjusted R-squared of 8355. It's better than what we saw, and you can do an adjusted R-squared comparison when we look at transformation here. It is significant, that's great, and all the p-values are significant at 5%, again, except for bath. Now what I'd like to do is an exponential when I take the log of rent, so I took the natural log ln of the value for rent over here. That's all I did. And I reran the regression with nothing happening to the x's. My adjusted R-squared went down a bit. My p-values, very interestingly, changed a little bit. In this case, only one is significant bed, but the model itself is significant. And the last one is try both. Well, let's take a log of rent and a log of square feet and see what happens. And you can see how we could try all kinds of things. We could have tried logging beds, logging baths, but the reason we messed around with square feet is because we saw that it had some logarithmic value to it. The others seemed to be the other way. They seemed to be somewhat linear. So in doing so, I end up with a model that has 85% of it is go back here. About 85 to 86% of that one, the log-log model, is being explained. Let me get back to it. So in this case, the adjusted R-squared is about 85. It's significant, and its p-values are significant, except for bath. And what this leads me to believe is bath is not a significant contributor to the regression, and I might want to take that out. We'll learn about that later. But in the end, I've run multiple regressions here, some multiple regressions, some log-log, some log, some exponential, just trying to figure out what model best fits our data. This is what statisticians deal with all the time, trying to find the best possible model to explain their data without overfitting. You end up with, as we saw, this grid. And in the end, while we do have the models, we have 3 explanatory variables. The standard errors don't make a lot of sense because some have been logged, transformed. But the R-squareds, particularly the adjusted R-squareds, can be compared. Now, simultaneously comparing error and R-squared doesn't make a lot of sense, but it does make a lot of sense to compare R-squared adjusteds. And you'd find that the models 2 and model 4 tend to perform the best, particularly model 4. And in the end, you could impute particular values, say, for example, 3 bedrooms, 2 baths, 1,600 square feet. I could do that for each, and I have this out here on Canvas for you to see. 3 beds, 2 baths, square feet. And for the first one, I added log square feet. I'm actually not using that. I'm just simply building the regression based on that, and I get a value of 1491. I copy this across. The next one, where we're log transforming square feet, you can see what I'm doing. Notice nothing happened with the y. That's why we're not seeing anything raised to a power. I get a value of 1540. The next one's going to require transformation. So the first thing I do, run the regression like you would normally do. I'm adding back in, as you can see, a value here, and this value is the standard error. I'm squaring it and dividing by 2. Then what I'm simply going to do is raise it up, e to the power of 7.34. The last one, very similar. I'm going to use and run the regression first. Run the regression first. Again, raising the standard error squared divided by 2. And then I'll take it and take the value e raised to that power. All those values are reflected here. Which ones of the models is most appropriate? It really depends what you're looking for. In our case, it would be the one that has the r squared adjusted with the highest value. The predicted values don't really mean that much because they're being based around a particular condition. If all three, bedrooms, bath, and square feet, fit within the range of those we're predicting from, it's fine. You're just looking for the model that best fits the scenario. For me, I would look at the one that has the highest r squared adjusted. That seems to be the one that has the best fit. Two of them are very close. In general, those two could be easily picked from. So that's where we say most appropriate. All those answers are completely appropriate because the models are significant. We've got multiple significant variables in most cases. That's chapter 16. The next thing we'll do is move on to our wrap-up as we move forward in some of the statistics classes. We move to the higher parts in chapter 17. For those that are done at the graduate level, we'll see and stop at chapter 16.